Hello students, good day. I hope all of you are well. In the previous couple of sessions, we discussed CPU scheduling algorithms that fall under the category of non-primitive scheduling algorithms. We discussed first come first served, shortest job first, as well as priority scheduling. From today onwards, we will discuss the second class of scheduling algorithms, that is primitive algorithms. And under this category, we have round robin, shortest remaining time first, and again priority scheduling that is of primitive in nature. It is interesting to observe that these three primitive algorithms, they are just variations of the algorithms that we have already discussed in the previous sessions. The first algorithm that we will discuss under this class is the round robin. A round robin can be seen as a primitive version of first come first served algorithm. As you know that this algorithm is primitive in nature, which means that once a process is executing in the processor, we will take out this process forcefully before it has completed its execution. So there must be some event that should be associated with this forcefully taking out of a process. Usually in round robin, this event is the time quantum. Time quantum is a particular time that we associate with the system, with the scheduling algorithm. And once that particular time slice expires, the scheduling algorithm takes out the current process from the processor and puts the new process into it. So in this way, the round robin forms a cycle of processes, and they get their burst time executed in the CPU in a cycle. So once a process gets the CPU time, it only gets it for a while. So once that time expires, the process is forcefully taken out from the processor and added to the ready queue. And another process that is selected by the scheduling algorithm, it is being placed in the processor. And again, when we have the ready queue, in the ready queue, processes form a queue, and that queue is based on certain characteristics. Once that queue is generated, the process that is taken out from the processor, it is placed at the end of the queue, and that is how a complete cycle is being formed. Usually when we have the round robin executed in a system, uh, there are processes that get equal amount of time from the processor. So usually this algorithm is useful when we have systems where we require some interaction, or we require some good response time from the system. Usually when we have round robin algorithm in place, no process waits more than n minus 1 into q time units, and this q is the time quantum. So you can see that if you are running in a cycle, no process has to wait indefinitely for other processes to complete their execution. So at least every process will get some chunk of the processor uh, before it completes it has to wait for the execution of other processes. So if you want to visualize the working of the round robin algorithm, just consider the first come first serve algorithm, and once a process that arrives in the system, it is being given to the processor, and after a while, after that time quantum expires, it should be taken out of the processor and it should be added to the end of the ready queue, and the process that arrived second, it should be given to the processor. So in this way, there is a cycle that is going on. There are several performance parameters that are associated with round robin. If that time quantum, if it is large enough that a process can complete its execution before that time quantum expires, so it will work like first come first serve basis. Usually we have a time quantum that is small enough that there are multiple context switches between multiple processes. However, we do not want to have a time quantum that is too small and most of the time is wasted in just the process of context switching. So over here we have an example from round robin. We have three processes P1, P2 and P3 having the burst time requirements of 24, 3 and 3 seconds respectively. The time slice or the time quantum for this example is 4 seconds. So now you can see that the processes, they arrived in the order P1, P2 and P3. So now you have to develop the Gantt chart where P1 will be given to the processor first, and once that time slice expires, P1 will be forcefully taken out from the processor and P2 will be given to the processor. Once either the time slice expires or the process completes its execution, that process will come out of the processor and the next process in the ready queue will go in the processor. So in this way, every process will get some of the CPU time. So please stop the lecture over here and try to develop the Gantt chart on your own and then continue later on. So here we have the Gantt chart. So as we discussed that P1, P2 and P3 entered the system in this order. So for the first 4 seconds, P1 will be in the system. Then once that time slice expires, P2 will enter the system. However, before the time slice expires, you can see that its burst time requirements are just 3 seconds. So P2 will come out of the processor once it completes its execution. So over here you can see that for P2, this round robin will act in exactly the same manner as first come first serve, because it completes its execution before the time slice expires. Then we have P3 that will enter the system at time interval 7 and it will leave it before the time slice expires. Again, for P3, this algorithm will act in the same manner as first come first serve because the time slice is larger compared to the burst time requirements of a process. So once both of these processes they complete their execution, so at time interval 10, we only have P1 in the ready queue. So it will be given 4 seconds from the processor. Once that time slice expires, it will be taken out from the processor and being placed in the ready queue. But because this is the only process in the ready queue, it will be given to the processor one more time. Again, after this time slice expires, it will be taken out from the processor and sent into the ready queue. But because this is the only process available in the ready queue, it will be again given to the processor. So it will continue to do so unless it completes its execution at time interval 30. This was the conceptual run that we had. However, we can have a couple of optimization to this technique. For instance, at time interval 14, there is no need to have to save the state of P1 and then reload it one more time because there is no other process present in the ready queue. So we can just check that is there any other process available in the ready queue. If there is any, we can have that context switching. If there is none, then we can continue with our execution of the same process. So these heuristics can be applied to any algorithm to optimize its performance. As you may have already observed, that a downside of round robin algorithm is the context switching time that is spent between the switching of two processes when the time quantum expires. In order to avoid it, it is desirable that the time quantum should be selected large enough so that important time is not wasted just in saving and loading the state of multiple processes. At the same time, we cannot have the time quantum long enough, as we will make this round robin another version of first come first serve, because if the time quantum increases the time that is required for the execution of a process, there won't be any difference between the first come first serve and round robin. This round robin algorithm usually has an advantage of better response time, because the first time when a process is scheduled for the processor, it is quite short compared to other algorithms. This is one of the reasons that this time quantum is selected quite carefully, and after spending some time on generating the test bed and running simulations based on the type of applications running on a particular system. All right, so moving on, we have several advantages and disadvantages associated with round robin algorithm. The first advantage is that in terms of response time, average response time, this algorithm is the best compared to all the other algorithms, because in this algorithm, all the processes they get response from the CPU after some time quantums. That is the reason that this algorithm is best suited for systems where we have multiple users sharing time of the CPU. It is quite commonly used in client server architectures as well as in systems which are interactive, because it is guaranteed by this algorithm that a particular time slot will be given to a process based on the number of processes running in the system. However, at the same time, there are some disadvantages associated with it as well. One is that it leads to a sort of starvation for processes which have uh, large burst times. Now, because it is possible that if we have, for instance, 100 processes running in the system and the time quantum is like 2 seconds, so every process will get its turn after 200 seconds. And if we have a process that has a large burst time requirement, which means that it won't be able to get itself executed quite often. It will get the CPU time for a while after all the other processes, but because the time quantum or the requirement for this particular process is quite high, that is why only a small burst of time will be given to it after the whole cycle. So this algorithm may lead to somewhat starvation for processes having larger burst times. Also, as we had discussed earlier, that the performance of round robin is based heavily on the selection of a suitable time quantum. If it is large enough, processes will complete their execution before the time slice expires, which means that it will act as first come first serve. And if it is short enough, then it will lead to more context switching, which means that useful time will be wasted in saving and loading the state of various processes. Some important aspects of this algorithm: if we decrease the time quantum value, we will have an increase in the context switching, which means that valuable time will be wasted in saving and loading the states of processes. However, when we decrease the value of time quantum, the response time of the processes, the average response time will decrease as well. Also, if we decrease the time quantum, the starvation chances will be reduced as well. However, by the increase of the same thing, we will have a reverse effect. If we increase the value of time quantum, this number of context switches will decrease, response time will increase, and the chances of starvation they increase as well. That is why this is quite a significant characteristics or parameter associated with round robin that has to be considered quite carefully. If the time quantum is large enough, then this round robin scheduling becomes first come first serve scheduling, as we had discussed earlier in detail. So that is why this should neither be too large or too small. So this there is quite a number of research articles that are there in the selection of a optimal time slice for multiple types of systems. So over here we have an exercise for you. In this exercise, we have 5 processes and they arrive in the system at different times. So you have to consider the arrival times while developing the Gantt chart, as well as while computing the average time for different processes. So P1 arrived at the system at time interval 0, P2 arrives at time interval 1, P3 arrives at time interval 2, P4 arrives at time interval 3, P5 arrives at time interval 4, while the burst time requirements are for P1 5 seconds, for P2 it is 3 seconds, for P3 it is 1 second, for P4 it is 2 seconds, and for P5 it is 3 seconds. And the time slice for the system is 2 seconds. So after every 2 seconds you have to switch the context and you have to put another process in the system. So now this is the exercise that you are supposed to do with round robin. I would suggest that you stop the video lecture right over here and work on your exercise and only continue once you are done. All right, so over here we have the Gantt chart. As you can see that at time interval 0, we have only one process present in the system, so the processor will be allocated to P1. So P1 will go into the processor for the first 2 seconds. At time interval 2, now we have two processes already present in the ready queue, P2 followed by P3. So when P1 will come out of the processor, it will go behind P2 and P3 in the ready queue, and then the processor will be allocated to P2. So for the next 2 seconds, P2 will be in the processor. At time interval 4, we again have P3, P1, P4 and P5. So P2 will go behind them. So P3 will be given to the processor. However, its burst time requirement is just 1 second, so it will complete its execution before the time slice expires. So at time interval 5, the state of the ready queue will be P1, and then the other processes are behind it. So P1 will be given to the processor. At time interval 7, P4 will be given to the processor for 2 seconds. At time interval 9, P5 will be the frontmost process, so it will be given to the processor. At time interval 11, now we have only 3 processes left in the system: P2 followed by P1 followed by P5. So P2 will be given to the processor. However, again only 1 second of execution is required by P2, so it will come out at time interval 12. At time interval 12, P1 will enter the processor and it will execute for the next 1 second. After it completes its execution at time interval 13, P5 will be given to the processor and it will complete its execution for 1 more second. So over here we have the Gantt chart that I assume that all of you have developed successfully. So now the next step is how to compute the waiting time for each of these processes as well as the average waiting time for the whole scenario. So over here we have waiting time for each of these processes. Remember that waiting time this time is the time that is spent by a process in the ready queue. So as you can see for P1, it arrived at the system at time interval 0 and it went in the processor at the same time. So it has not to wait for any time. However, when it came out at time interval 2, now it is in the ready queue waiting for its turn after the execution of other processes. So for 2 seconds P2 was in the processor. For 1 second P3 was in the processor, and then P1 again got its slot. So for these 3 seconds P3 was waiting in the ready queue. Again over here when we have this time slice expires, P1 was again in the ready queue. So it has to wait for these 2 seconds, these 2 seconds and this 1 second, which means that now it has waited in the ready queue for another 5 seconds. So 3 seconds over here and 5 seconds over here will produce 8 seconds, a total waiting time for P1 in the ready queue. Over here P1 completes its execution at 13. It arrived at the system at time interval 0. So the requirement for P1 was 5. It means intuitively that it has spent 8 seconds in the ready queue. In the very same manner, you can calculate the waiting time for other processes as well. So the average waiting time for this scenario is 5.8 seconds. I hope there is no confusion for the whole thing, the Gantt chart as well as the calculation of the average waiting time. We have done this probably a couple of times already. Alright students, so moving on, we have the next algorithm, that is shortest remaining time first. This is the second algorithm in the primitive class and it can be considered as the primitive version of shortest job first. If you just focus on its name for a while, shortest remaining time first, you will come to the conclusion that this algorithm calculates the remaining execution time for each of the processes and it selects a process which has the shortest remaining time left. So after the expiry of every time slice, it looks in the ready queue and selects a process that has the shortest remaining time left to complete its execution. Like I mentioned earlier that this algorithm can be considered or can be seen as the primitive version of shortest job first. So just like shortest job first, in shortest remaining time first, we can have starvation problem for longer processes. So again, if we have a longer process, it will keep on waiting for all the short processes to complete their execution first. So over here we have an example for shortest remaining time first. As you can see that over here we have four processes: P1, P2, P3 and P4. P1 arrives at the system at time interval 0, having a burst time requirements of 8 seconds. P2 arrives at the system at time interval 1, having a burst time requirements of 4 seconds. P2 enters the system at time interval 2, having a burst time requirements of 9 seconds, while P4 enters the system at time interval 3, having a burst time requirement of 5 seconds. So we have these four processes, and we have to see how they work in the system under the shortest remaining time first algorithm. Here we have the Gantt chart. As you can see that at time interval 0, we have only one process present in the system. So the processor will be allocated to P1 and it will start its execution. At time interval 1, when the time slice expires, now the scheduler will look into the ready queue and it will observe that we have two processes in the ready queue, P1 and P2, and their burst time requirements are 7 seconds. As this P1 has elapsed 1 second already in the CPU, so the remaining time will be 7 seconds and 4 seconds. As the algorithm has to pick the shortest remaining time, so P2 will be selected and it will be passed on to the processor. At time interval 2 over here, uh, the scheduler will again look into the ready queue. Now we will have three processes in the system: P1, P2 and P3. P1 has the burst time requirements of 7 seconds. P2 has the burst time requirements of 3 seconds, while P3 has the burst time requirements of 9 seconds. Again, the shortest remaining time algorithm will pick up P2 for its execution. At time interval 3, now we will have all the four processes in the system: P1 having 7 seconds, P2 having 2 seconds, P3 having 9 seconds, and P4 having 5 seconds. So over here at time interval 3, the scheduler will again pick P2 and put it into the processor. For the remaining slices, as there is no change in the system and with every elapsed time slice, P2 will have reduced remaining time, so P2 will complete its execution in the processor. At time interval 5, when P2 completes its execution, at this point we have three processes in the ready queue: P1 having a requirement of 7 seconds, P3 having a requirement of 9 seconds, and P4 having a requirement of 5 seconds. So as P4 is the shortest, so it will be given to the processor. So it will again complete its execution in the processor unless it completes its execution. So at time interval 10, we have two processes, P1 and P3, having a requirement of 7 seconds and 9 seconds, So P1 will enter into the processor. It completes its execution at time interval 17, and then P3 will complete its execution at time interval 26. Now again you have to find out the waiting time for each of the processes as well as the average waiting time for the whole system. Once again, for P1, you have to calculate the waiting time that P1 has spent in the ready queue. So over here we have the average waiting time. So you can see that P1 has completed its execution at time interval 17. It arrived in the system at time interval 0, and the requirements were 8 seconds. So it means that it has spent 9 seconds in the ready queue, and you can calculate it with the Gantt chart as well. And the rest of the processes, you can calculate the waiting time for each of them in the very same manner. So the average waiting time for the whole system is 6.5 in this particular scenario. So over here we have a class exercise. In this exercise we have 4 processes, P1 to P4, arriving at the system at time interval 0, 1, 2 and 3, and having a burst time requirement of 7 seconds, 3 seconds, 8 seconds and 4 seconds respectively. So you are supposed to develop the Gantt chart for this scenario as well as calculate the average waiting time for the whole system. So please stop your lecture over here and continue once you complete your exercise. So here we have the Gantt chart. As you can observe that at time interval 0, we have only one process present in the system, P1. So the processor will be allocated to it. After the time slice expires at 1 second, the scheduler will find that there are 2 processes in the ready queue, that is P1 and P2, having burst time requirements of 6 seconds for P1 as 1 second is already elapsed, and 3 seconds for P2. As the algorithm is shortest remaining time first, so the scheduler will select P2. At time interval 2, the scheduler will find that there are 3 processes in the ready queue, P1, P2 and P3, having requirements of 6 seconds, 2 seconds and 8 seconds. As before, P2 has the shortest remaining time, so it will be given to the processor. At time interval 3, again the scheduler will look at the ready queue, find all the 4 processes, and once again P2 has the shortest remaining time left, so it will be selected one more time. At time interval 4, when P2 completes its execution, the scheduler will see the ready queue and find P1, P3 and P4 in the ready queue, having requirements of 6 seconds, 8 seconds and 4 seconds respectively. As you can see that P4 has the shortest remaining time, so it will be selected and given to the processor. At time interval 8, we have only 2 processes left in the ready queue, that is P1 and P3, having requirements of 6 seconds and 8 seconds respectively. As the shorter one is P1 this time, so it will be given to the processor. At time interval 14, P3 is the only process that is available, so it will enter the processor and complete its execution at time interval 22. So now once we have the Gantt chart, now it's a bit easier for us to compute the waiting time for all of these processes as well as the average waiting time for the whole system. So over here we have the average waiting time for all the processes. As you can see, for P1 it completes its execution at time interval 14 and the requirements were 7. So it means that it spent 7 seconds in the ready queue. Also from the Gantt chart you can observe that it has to wait in the waiting state when P2 was running in the processor for 3 seconds. Then when P4 was running in the processor for 4 seconds, again P1 was in the waiting state. So 3 plus 4 yields 7. That is the waiting time for P1. So likewise you can compute the waiting time for all the other processes as well. So the average waiting time for the whole system is 5 in this scenario. Alright students, so that is all for today. In today's class we discussed two primitive algorithms. The first one was round robin and the second one was shortest remaining time first. I hope that you have understood both of these algorithms. In the next session we will try to conclude this scheduling algorithm section. Thank you students, stay safe.